Section 13.4 is Green's theorem. This is yet another analog to the fundamental theorem of calculus. So what we'll need to define first is a positively oriented curve. So remember that a parametrized curve has a direction. That would be the direction of increasing parameter. So often t is the parameter. So as t goes from 0 to 1 or 0 to infinity, or t just moves in a positive direction. However, our points on the curve are follow that positively trending value of t is essentially the direction of the curve. A positive orientation is one that travels clockwise around a simple closed curve. So down below we've got a simple closed curve C here, and it's traveling in a counterclockwise direction. That's our positive orientation, is a counterclockwise direction. It's indicated by this arrow here, and that just means as our parameter increases, our points are formed in that direction along this curve. Okay, and that's opposed to a non-positively oriented curve or a negatively oriented curve, which would be traveling in the opposite direction, moving clockwise. Okay, another way to think about it is if we're a positively oriented curve, as we travel C, we keep the region that we bound, D, on our left. Right? So the inside of this is always on the left of this curve. So that's a positively oriented, simple closed curve, and that's the basic object of Green's theorem, as well as the region D that such a curve encloses. And if we have such a curve, positively oriented, piecewise smooth, simple closed curve in the plane, and D is the region bounded by C. And then we have P and Q with continuous partial derivatives. P and Q, we'll remember, are essentially the x and y are first and second components of a vector field F, so functions of x and y. And if they have continuous partial derivatives on some open region containing D, then we have Green's theorem as follows. The line integral of F, or split apart written as P dx plus Q dy, is equal to the double integral over D of partial Q with respect to x minus partial P with respect to y. So the line integral along C, right, is equated to this double integral over the region D for this difference of partials right here. Now, the reason this is, or we can see that this is similar to a fundamental theorem of calculus, again, because the whole game with these fundamental theorems is to eliminate an integral, right? And we notice we have a double integral of derivatives of functions on the right, and on the left we have a single integral, and those derivatives are gone. So in some sense, we can think about Green's theorem being the cancellation of this integral with these derivatives, these partial derivatives. So that's the essence of Green's theorem, and it's yet another extension of the fundamental theorem of calculus. Some notation that we'll see: this circle on the integrand is, or integral sign is used to denote the line integral of these functions P and Q in the positive direction, or the positive orientation of the curve C. Also note that this partial D, or this script D, capital D, is used to denote the positively oriented boundary of the region D. It's not any kind of derivative or anything. It's just a symbol for the positively oriented boundary of a region. We'll see that notation come up quite a bit. So let's have an example first. So we're asked in the first example we're essentially going to kind of verify Green's theorem here. They ask us to evaluate this line integral given first line here, over the region, or the triangular region with vertices given as this, where we travel from 0, 0 to 3, 0 to 0, 1 and back to 0, 0. And they ask us to do this directly as a line integral, as we see here, and also to do it via Green's theorem. This is just to kind of confirm that it's true in some sense, at least for a specific case, and also to show the utility of it. Sometimes, a line integrals, it can be kind of a mess to put together thanks to all the parameterization, and Green's theorem gives us a nice quick out if we have a nice way to express it as a double integral. So that'll all be dependent on the problem that you've got at hand at any given time, but let's have a look in this case. So the direct method, just calculating the line integral as is, we form the triangular region for these 3 points. And really this problem, it doesn't quite give us a direction of travel, but since it lists these points in this order, 0, 0, 3, 0, 0, 1, we're going to assume that's our order of travel, from 0, 0 to 3, 0 to 0, 1, and then we close the region up by going from 0, 1 to 0, 0. So we see off to the side, I've graphed this, 0, 0 to 3, 0, then 3, 0 to 0, 1, then 1, 0 to 0, 0. Okay, those are our 3 paths. These are all line segments since it's a triangular region between these 3 points. So we use that R of t equals t times the first point plus 1 minus t times the second point, and that gives us each of these line segment parameterizations between all 3 of these points. And we've got them labeled over in the graph on the right so you can see which one's which. Now for the line integral, we know that if it's piecewise smooth, which it is, it's made up of R1, R2, and R3. So for these piecewise smooth pieces of it, essentially, we can split the integral into three integrals overall. So these are the 3. Now the first is R1, second line is R2, third line is R3. And what we're using in each of these cases now is the fact that x for the first integral is 3t because we're on R1. So 3t is used in this formula here. We have 3t times y, which is 0. And that's where that 0 comes from. Similarly, if we look at x squared, the q portion of this, x squared is 3t squared. Now dy is the derivative of y with respect to t dt, and that's the derivative of 0. So we have this 0 dt. So the whole first integrand or integral just zeroes out. So R1 doesn't contribute anything in this situation. The second one, just to map out one more, and I think the reader, has enough practice with line integrals at this point to have seen this even on their own, but just as a refresher, we'll do one more. This is the R2 integral. Again, in all 3 cases, we should note we go from 0 to 1. That's the way we built these parameterizations. We use that standard line segment parameterization. So that's why t ranges from 0 to 1 in all cases. Now, xy is 3 minus 3t times t. That's this term. And then times dx dt dt. So the derivative of x with respect to t is negative 3 times dt. So that's putting together the p dx version of this in the line integral. And the q dy is now x squared dy. So x squared is this term squared. And then dy is dy dt dt. So the derivative of this with respect to t is 1 dt. So that's our second integral. And if the reader checks the third one, we'll see that that one also goes to zeros as well, and that's using this parameterization here. So there's really only one integral to handle. Everything's in terms of t, and that's the trick to a line integral, is to get everything onto a single parameter t and integrate through that. Once we take care of that work, we end up with an integral that looks like this, and our answer is 3/2 in the end. It's a pretty straightforward polynomial integral or antiderivative. So that is the direct method, calculating the line integral. Of course, it's tedious and there's a lot of room for mistakes in this. So let's have a look at Green's theorem, which gives us an option to solve this. So doing this in terms of Green's theorem, we use the right-hand side of Green's theorem on the previous page, so the double integral instead. So what we're considering now is the integral of this function, or sorry, the integral of the partial derivative relationship of this function. We'll see that in a moment down at the start of that problem, over this region. So we do this as a typical double integral. We need to find the boundaries of the variables along that triangular region, D, and put that as our limits of integration, and then integrate the functions that we need to integrate. The functions we need to integrate are these two. Partial of q with respect to x minus partial of p with respect to y. Remember that from the problem above, p is xy, q is x squared. So our partials look like partial of p, q with respect to x is 2x, partial of p with respect to y is x. So the difference of these two is 2x minus x in our integrand. Note that we've already put together our region D. X is bounded by 0 below. It's bounded above by the line y equals 3 minus, okay. Yeah, 3 minus 3y. So it's x is bounded on the left by x equals 0, and it's bounded on the right by the line 3 minus 3y. So what we're doing is we've got slices that look like this, if we remember back from chapter 12, horizontal slices, horizontal bounds for these x variables. Okay, and let's see further. Then y ranges from 0 to 1. Of course, that's pretty easy to see in the graph. So our double integral is set up. We have our integrand, partial q minus partial p, and moving along, it's a pretty straightforward integral. It's the integral of x, the antiderivative of x, so we get 1/2 x squared, that's with respect to x, and then evaluate from 0 to 3 minus 3y. This introduces a more complicated polynomial in the integral. However we care to go about doing that, a u substitution might be helpful. We could expand it either way, and we continue to finish with another value of 3/2. So what we've confirmed is that in either case it works. It's no proof of the theorem, but it might give us a little bit of reassurance that it seems to work out for these cases we might look at. And it also, I think it demonstrates the utility of such a theorem. I would much rather handle the work down here, especially because we put a lot of work into chapter 12 to learn how to do these double integrals, than I would deal with all these parameterizations and the possibility of getting something wrong in the direct method. So let's see a sketch of the proof of Green's theorem. Okay, this will just help us sort of understand where this comes from and why it does what it does. So we let D be a simple region in R2. That is a region in the plane in which it's both type 1 and type 2. So remember back to chapter 12's description of that. Type 1 and type 2 means it can be bounded by, in this case, functions h1 of x, h2 of x. Y ranges between two such functions vertically, and then between two constants on the x-axis. Type 2 is the opposite. Type 2 means y is bounded by two constants, c and d, vertically from c up to d, and then side to side the region is bounded by functions of y, g1 of y on the left, g2 of y on the right. So to prove Green's theorem, we just note that we could simply independently show that this equality holds and this identity holds as well. Okay, and then if we add them together, if we add the two left-hand sides, we'll get the line integral of Green's theorem, and when we add the two right-hand sides, we'll have the double integral of Green's theorem, and we'll have the whole thing all together. So breaking it into pieces is the way to go, and what we'll prove is the one on the right, just for arbitrary choice's sake. Now, if we want to prove the one on the right, we're going to use the fact that our simple region can be expressed as a type 2 region. So what I've sketched off to the side is exactly that, a type 2 region here, where y is bounded by constants. So it's sort of I might call it semi-rectangular, right? We've got two straight line bounds, horizontal line bounds, a value of c and a value of d. Okay, this upper c I should be careful with. That was meant to denote the simple closed curve c for all of this, so maybe I'll call it that. It's a little clearer. C as a bound is down here as a y value, and d as an upper bound is there as a y value as well. Now we note that x is bounded between g1 of y and g2 of y, and that's exactly the case for a type 2 region. So with that in hand, let's have a look at both sides of this identity, and let's build a bridge to make them match. In other words, let's make them equal to the same thing, and then we'll be able to declare that they're both equal to each other. So starting with the double integral over d, we can express that as follows here. Some language I'm going to skip over because I've more or less said it. That the double integral over d of the partial of q with respect to x is an integral with these bounds since it's type 2. Okay, and now if we sort of zero in on partial of q with respect to x, our first integration is with respect to x. It's on a function whose partial derivative has been taken with respect to x. So essentially what happens in here, or exactly what we do in here, is we use the fundamental theorem of calculus part 2, right? We're taking the integral of a derivative with respect to the same variable. So that yields the evaluation of this function q at the upper endpoint minus at the lower endpoint, or at the greater endpoint minus the lesser endpoint in the limits of integration. That's exactly what we see to the right. The first integral c to d stands with respect to y, and we've evaluated the inner integral to be q of g1y minus q of g2y, comma y in both cases, and then with respect to y. So that reduces to a single integral of this difference of the function q. Now let's see if we can make the left-hand side look like that. So for the left-hand side, we're thinking of a line integral, okay? And that's the line integral along this region C. So we're positively oriented the way we have it written here, okay? Now, as we move the variables in their sort of natural way, we're going to integrate along C1, and then we'll integrate along C2. We're still going with the flow, right? Well, when we integrate along C3, we go from left to right, and we're going in the opposite direction of the orientation of the curve. So that's actually negative C3, and something similar for C4. We integrate C4 from C to D. Right, we're going in the opposite direction of the orientation of the curve. So both of those will have a negative next to them. It'll turn out that C1 and C3, since y doesn't change along these curves, dy is 0. So our C1 and C3 integrals are 0. Right? We have no change in y value, and since we're integrating with respect to y in each of these, there's, dy is 0 in that sense, so there's nothing to pick up there. So each of these two just integrates to 0 thanks to the constant nature of that part of the curve. Now for C4, we've made the note off to the side that when we integrate along C4 and we want to add it to the order in which we're going to move along this line integral, we realize that we're going to have to move in the negative direction of C4. Well, the integral along C4 is negative the line integral in the opposite direction of C4, and that gives us, well, from C to D, this negative integral here for C4. Okay, very similar. C2 is just the positive version of itself. When we move positively along it, it's going with the direction of the curve, so it remains positive as an integral. It's from C to D of q of g2 of y dy. And now we need to add these two integrals together. So we made a note of C2 here. And when we add these two integrals together, along with these two, which sum to 0, so we've got 4 line integrals that add up to be the integral C, or the line integral along all of C, and 2 of them are 0, and this one's negative, the other one's positive. When we add them together, we end up with the whole line integral being the positive one minus the negative, minus this one, or the G1 version, and we get exactly this statement right here. That matches perfectly with the result we got for the double integral. Since that's the case, we can conclude that this double integral is equal to this line integral, and that is exactly the identity we wanted to show. Now for the other identity in this that we don't do, you follow a very similar procedure. Now you just assume that D is a type 1 region, or you write D down as a type 1 region, which is completely viable because we've assumed that it is. It's a simple region, which means it can be expressed in either way. So note that our picture doesn't really show that. I've emphatically drawn this as a type 2 region just to help us see our way through this path. That's certainly not a type 1 region, but since this simple region satisfies both, we can just re-sketch it as if it's a different looking region. Again, the picture is just a heuristic. It's not actually the real situation here. The book also has, I believe, the proof for the other identity that we didn't do, and maybe some more details that might be left out here. So that's it. It's just a simple follow the line integral as you expect you would, and compute the double integral and see that they're actually both equal to each other. I guess one key thing was to split the both portions of it up and show two different identities to add together. Okay, let's get back to using it. We can calculate area with Green's theorem. That's kind of a nice fact about it. So if we recall this identity to find the area of some region D in the plane, we use 1 as our integrand. Now, if we can find functions P and Q, which satisfy this identity right here, well, then we can use that to use a line integral to calculate the area within some region or bounded by some simple closed curve C or boundary of D, whatever it is we might be looking at. So 3 such functions are these. Okay, x 1/2 x minus y. And we're asked below in the first example to confirm that the line integral to compute the area enclosed by this simple closed curve C, we're asked to show that these formulas actually work out and satisfy this identity. I only do one. I just arbitrarily chose the first one. And we realize that Q is x and P is 0, right? There's no dx in this formula, so there's no P showing up in here. Now, does this satisfy this identity? It turns out it does. The partial of Q with respect to x is 1, partial P with respect to 0 is 0, and their difference satisfies the identity, or equal to 1. So it's a nice, simple calculation to put together. Of course, we can come up with more complicated ways of doing it, and there are 2 more to show, but the reader will find that both of these hold, as of course we would expect. So let's make use of it real quick. So find the area enclosed by the ellipse. This is kind of a cool calculation. Many readers have probably not seen the formula for the area enclosed by an ellipse. The book does a general example where this is an a squared and this is a b squared below, which means we could calculate the area enclosed by any general ellipse. Anyway, let's have a look at a more specific case. So we let C be the ellipse parameterized by, it looks like 2 cosine t, thanks to a being 2, and 6 sine of t, thanks to b being 6, the square root of both of those denominators. And we let t range from 0 to 2 pi. Now we're parameterizing the ellipse in a single variable t because, well, of course we want to use this line integral formula up here. Okay. Maybe the reader should consider as a second exercise, can you use a double integral to find the area enclosed by this ellipse? Of course you can. It might be more or less easy than this method. I believe this might be the easier one though, if I recall correctly. So let's arbitrarily choose one of the formulas above. Again, I just choose the first one. I like it. It doesn't have any minus signs in it. And I don't think that it's going to, make this problem any harder or worse than any of the other formulas would. Of course, you have 3 choices above and really many more if you wanted to build your own to, as long as this identity is satisfied, to calculate these areas. So setting it up, A is equal to x, 2 cosine of t, times dy. Now dy, let's recall, I'll put in some extra notation here, just so we're not lost on anything that's happened. Remember that dy is equal to dy dt dt. So when we convert from one differential to the other, we're doing it through a chain rule essentially. And this is what we see here. Dy dt is the derivative of this function with respect to t, and that's 6 cosine t dt. And we're off and running. We've got 2 cosine t times 6 cosine t, so that's 12 cosine squared t from 0 to 2 pi. Remember, we want to trace out that entire ellipse. So we're going from 0 to 2 pi. And the antiderivative of cosine squared t is 1/2 t, 1/4 sine 2t, all times its constant. Evaluation at the endpoints. Well, sine of whole number multiples of pi is 0, sine of 0 is 0, so that term contributes nothing. We have 1/2 2 pi minus 0. We get pi times 12, so we've got 12 pi. It's interesting to note that the full formula for the area of an ellipse is actually pi times a times b. So pi times 2 times 6 in this case for 12 pi. And that's what the book shows in its example. Kind of a neat fact. So let's see what we can do if we don't have quite a simple region. So if we have a finite union of simple regions, then we can still apply Green's theorem, and let's see how that works. So this is nice because it extends Green's theorem to account for more regions than just the simple region D that we've defined before. So if we're given a region D now that is the union of two simple regions, D1 and D2, such that D1 has boundaries C1 union C3, simple closed curves, simple closed piecewise smooth curves, and D2 has boundary C2 union negative C3. Well, that's what we're going to assume to start with to show how this works. Now, here's our region D, and it is the union of D1, which is this curve, traveling it clockwise. We have C1 in the positive direction, C3 in the positive direction, and then we've got also D2, which we travel C2 in the positive direction, and so that way we're traveling the whole curve overall in the positive direction. But in order to continue in the positive direction, we have to travel C3 in reverse. So D2 we see has boundary C2 union negative C3, and that's why this comes about. Okay, so if we're to calculate those line integrals, then we've got to remember to do C3 in reverse, because that's how we are putting this region D2 together. So Green's theorem applied to each one of these simple regions, D1 and D2, are the following. We see all the notation of Green's theorem happening within the integral, so I'm just pointing out what the limits of integration are. And we see that, yes, in fact, we are running C3 in reverse. Remember that the line integral over these two unions would actually split as the sum C2 plus negative C3, right? And that's how the unions come about. When they split up, if we were to add all of these together, remember the one up here is C1 plus positive C3. If we add all of these together, well, we would also want to remember that negative C3 is really, or in the negative C3 direction, is minus C3 in the positive direction. So when we added them up, we'd get C1 plus C2 down below all of this. And that's in fact what happens in the work below. This is just a shorthand off to the side here, nothing official, but it gives us an idea of what's happening, why we arrive at this, C1 union C2. So we can just follow the outer curve C1 and C2, and we're equal to the double integral over the entire region D. That's quite nice. So what we can do when we need is to split up a region D into line integrals about simple regions, and we'll know that this region D can just be integrated as a double integral directly thanks to Green's theorem. So again, to kind of restate that and clarify what's going on, if we have a region that can be split up into simple regions, and we see that that exists, we don't need to do anything with it. We don't need to calculate the line integral of these. We can just commit to this full region D with boundaries C1 and C2, and just take the double integral over the entire region. So let's see how that goes in a problem, just to be even clearer. So we're asked to evaluate the given line integral here, where C is the boundary of the semi-annular region in the right half plane between the circle with radius 1 centered at origin and then the circle centered at the origin with radius 2. Okay, square root of 4 is 2. Okay, so that's been drawn as follows. It's in the, oh, it says the right half plane. I've done the, let's correct it then. I've done the upper half plane, so that was a mistake. But we'll correct the notes to do the correct, to do what I've done in the picture here. The right half plane would be similar, just obvious changes made where needed. So that would mostly be in the angles that we use. Now what we need to realize is that this is not a simple closed curve, right? It's not simply connected. Okay, a path from here to here, line segment doesn't join them. Okay, so we've got a bit of a problem here, right? But what we'll note is that we have a boundary on the y-axis here that we can just insert. So we can think of this full region D, the entire semi-annular region here, as being two regions, and they're split like this. So now we've got these two simple regions, and I misclassified this. It's not simply connected. I'm sorry, this line segment idea is not the matter. It's that it's type 1 and type 2. Okay, so that was a mistake on my part. So let me just show again that that's not the case though. The full region D is not. It looks like it could be. It can easily be type 1, right? We see that. So type 1 would mean that the x values are bounded by curves along the y-axis, and that it could be rectangularly bounded. Well, yeah, and then it's bounded side to side. See, the problem we run into for our horizontal bounds is this, right? This is a complicated region down here in the lower portions, right? So we're not type 2 or type 1 because of that, all right? But what we have overall when we split the two is we have regions that can be described that way. Really, what's the problem that's causing all this, it's not both type 1 and type 2 because this gap in here prevents that from being the case. The regions are more complicated than that. If we look at a single one, right, then we realize that this can certainly be written as a type 1 and type 2 region. So that's why we have to think about clipping this apart. But again, we don't need to do much with adding in that extra border. All we need to do is realize that it can be done, and it splits these two into simple regions, each on their own. And if that's the case, it means that, sure, such a line integral would exist, but we don't need to worry about it. We can just use the full double integral over the region D. And in setting that up well, of course, these two functions, partial q with respect to x and p with respect to y. There's p, there's q. And our line integral over the whole curve C, which is the boundary of this region D, knowing that we can split it up, we just sort of jump through that work to go directly into our double integral. And we see that we go from 0 to pi to catch these angles here, and our radii go from 1 to 2 to fill in that band. And we're often running with a polar integral, r dr theta, don't forget about that. And partial q with respect to x is 3y. Partial p with respect to y is 2y. So here's 3y minus 2y from this expression. And once the reader sees all of that, we should be good to go from there. And we come out with 14 over 3 using standard procedure from there. Okay, so once you realize that the region can be split into two simple regions, then you don't need to worry about how you split it or splitting it or even thinking about the line integral itself. Once you know it can be split into these regions or see a method for doing that, you can jump straight into the double integral and go from there. So that's the point of most of the above work up here. Okay, so let's look at a work example. So we get more deeply into this. So we're asked to use Green's theorem to calculate the work done by the force F, given as P and Q in this vector field, in moving a particle from the origin 0, 0 to the point 0, 2 on the y-axis, then to the point -2, 0 along the line segment between these 2 points. It's important to know what path they're telling us it needs to travel, and then back to the origin along the x-axis. So everything is done as a line segment. So origin to 0, 2, 0, 2 to -2, 0, and then -2, 0 back to the origin. So that's our path. Our line integral could be parameterized and set up, as usual, as in previous sections. And we'd be looking at the line integral of this function. We need to convert everything to a parameter t. And it's a lot of work. It's 3 different integrals we'd need to do. But we have Green's theorem, right? So Green's theorem tells us that this line integral is equal to this double integral if this is a simple region D, which in fact it is. It can be considered as type 1 and as type 2. So we're all set there. And what we've done is we've essentially expressed D as, it looks like, a type 2 region. Sorry, I had a moment there. Type 2 region because Y is bounded by functions of X. Actually, it's a type 1 region. Okay, whatever. It's one of the types. And Y is bounded by this function below and this function Y equals 2 minus X above. And then X is bounded by 0 and -2. So -2 to 0 along the x-axis. And once that's together, we have a pretty straightforward polynomial double integral here. And computing the details of that, we get 80 over 3. So note at the very beginning that the work is equal to the line integral of f dot dr along C, which is exactly our p dx plus q dy line integral for this, this force field F equals pq in vector components. And that's how all that comes about. Once we have this line integral, if we don't like the look of it and don't want to do the work of all the parameterizations, we note that Green's theorem gives us an out to consider the double integral. Which is interesting because you would think that probably since Green's theorem reduces the number of integral signs or integrations you have to do, you'd probably tend to favor the line integrals, but the line integrals come at the cost of all these parameterizations. It's just nice to have an option either way. And we'll note that in problems we've done in this section, we've chosen a line integral or we've chosen the double integral, one way or the other as directed by a problem, and in the future we'll just do it out of convenience. So it's a very nice result to have in our back pocket. Okay, lastly, this is a promised result from the previous section, I think 13.3. Use Green's theorem to prove that if the vector field F equal to PQ is such that P and Q have continuous first partial derivatives and are equal to each other, then F is a conservative vector field. Okay, so let F and P and Q be as stated in the theorem above, and let C be any simple smooth closed curve bounding some region D. And we'll assume that these partial derivatives are continuous in some broader region containing D, for any closed curve C that we consider. Okay, now we know that this identity holds. Okay, and that being the case, we'll use Green's theorem to write down what that means. It means that the line integral along C of f dot dr, which is our P and Q line integral along C, just splitting it up into its vector components, P and Q. By Green's theorem, right here, we know that this line integral is equal to the double integral of this partial derivative difference. So this is just Green's theorem from page 1 of these notes written down, but we know that these two are equal to each other, stated in these spots here. So this is the integral of 0, which is 0, which overall says that the line integral, this, is equal to 0. So, and that's for any simple closed curve. Note that we chose some simple, smooth, closed curve bounding some region D. We made no other assumptions about it other than the continuous first partial derivative hypothesis holds for any closed curve that we choose. And so that's exactly the definition of F being a conservative vector field, or a characterization of F being a conservative vector field, is that the line integral along any path C is equal to 0 for a closed curve. C, I should say, not any path C, but any closed path C. So there we have the result that we were using in the last section to determine whether or not F was a conservative vector field. And that's it. That closes up section 13.4. Green's theorem is a very nice tool. It lets us relate the boundary, the line integral of a boundary to the double integral of the region enclosed by that boundary. And it's yet another generalization or analog to the fundamental theorem of calculus.